Hello everyone, this is Vipul Purohit and I welcome you to my YouTube channel. My dear friends, here I'm going to discuss about the very key features about applied electrochemistry, which is a part of TYBSc semester 6 syllabus. So here we begin with the types of cells. Now primarily there are two types of cells, chemical and concentration. Chemical cells are the cell in which the free energy due to chemical reaction is converted into electrical energy. When you talk about concentration cell, in this cell electricity is produced by the decrease in the free energy, which is because of the mass transfer between the two cells. As you all know that mass and energy are related by means of Einstein's equation. So this is what happens in concentration cell. Now if you go for a flow sheet diagram with respect to the types of cells, here it is. Basically they are being classified into two categories, chemical and concentration cells. Chemical cells are of two types, without transference and with transference. Concentration cells are of two types, that is electrode as well as electrolyte. When you talk about electrode cells, it is reversible to cation and the other one is reversible to anion. When you talk about electrolyte, it's once again being categorized into two parts, that is with transference and without transference. And in both the cases, we further classify with respect to reversible to cation and reversible to anion. So this is, my dear friends, about classification of cells. So there is a possibility of question being asked that discuss the classification of cells. So this is what the sketch that you can put forward. Now we go with the first case, that is chemical cell without transference. The chemical reaction taking place at the two half cell is converted into electricity in a chemical cell. Okay, this is the basic principle behind this cell. Now, when you consider the requirements, the first one requirement is both the electrodes must be different. Second one is the electrolyte is common. One of the electrode is reversible to the cation and the other one is reversible to the anion. Now, let us consider a following cell where we consider a platinum electrode. Okay, now one of the side, as I said, the two electrodes must be different in terms of not the composition but in terms of the content part. So we have a platinum electrode and it's going to be in contact with the hydrogen gas and sulfuric acid, mercury sulfate, Hg and Pt. Now here what happens is, this is the cell which contains a common electrolyte acid is mentioned in the requirement, that is sulfuric acid, and it is made up of a hydrogen, that is H2, and a metal insoluble salt electrode, which I am referring to Hg and Hg2SO4. The former electrode, that is the Pt and the H2, is reversible to the cation, and the later one, that is Pt along with the Hg2SO4 and Hg, is reversible to the anion. Now here we discuss about the half cell reactions taking place, that is a reaction taking place at the left hand side and the right hand side. Now, my dear friends, let me be very clear. On one side, that is basically on the left hand side, the oxidation reaction takes place, that is loss of electron. And on the right hand side, the reduction reaction takes place. And also please remember, the number of electrons lost is equal to the number of electrons gained, and as a result of which, when you write down the net cell reaction, the net cell reaction is a summation of the left hand side reaction and the right hand side reaction. You don't have any electrons because the electrons gets cancelled out. So here we go. In the left hand side reaction, we have oxidation reaction where a hydrogen gas gets converted into a proton, that is an H plus ion, by the loss of two electrons, which are being gained at the right hand side electrode by means of Hg2SO4, and that results in the formation of a mercury metal and the sulfate ion. So the summation of the two reactions, as I said, will give you a hydrogen gas with Hg2SO4, that is mercury sulfate, and that's going to give you mercury metal, a proton and a sulfate ion. Now let's try to apply a Nernst equation for this. You know what the Nernst equation is? It's E cell is equal to E naught cell minus of 0.05916 upon N. Now what does 0.05916 is? Yes, my dear friends, it's 2.303 into R into T upon F. R is a gas constant, which you know the temperature is the value of which is 8.314. T is the temperature, which is considered as 298 Kelvin. F is Faraday of electricity, which is 96,500. And N stands for the number of electrons which are being cancelled when I write down the net cell reaction into the log of activity of the product upon the activity of the reactant, which we consider in the net cell reaction. So here we have the net cell reaction, you know very well. So we have activity square of Hg, because there are two Hg, into activity square of H plus into the activity of sulfate ion, divided by the activity of the hydrogen gas into the activity of mercury sulfate. Now what we have is the two electrons are being cancelled out, so we substitute the value of N as 2 and we get the final reaction, that is the Nernst equation, which says that E cell is equal to E naught cell minus of 2.303 RT upon 2F, okay, into log of activity square of Hg into activity square of H plus into activity of sulfate ion, divided by the activity of hydrogen gas into activity of mercury sulfate. All right, so this is, my dear friends, I hope you have understood this. Now we're going to the next part, and that is chemical cell with transference. Now chemical reaction taking place in the 2-half cell is converted into electricity. In this cell, two different electrolytic solutions are in contact with the two different electrodes. I hope you understood the difference, my dear friends. In the previous case, we had an electrolyte common, and that was H2SO4. Now here in this case, we have got two different electrolytes. So consider the cell where we have a zinc metal or a zinc electrode which is being dipped in a zinc ion solution, and at the same time I have a silver ion solution into which is dipped this silver electrode. Now since the two electrolyte solutions are different, the mobility of the ions are also different, and this results in a junction, and this is known as what? A liquid junction. Now the difference in the speed of the ion results in a potential. Okay, because there's going to be a potential difference, and that potential difference which is going to be developed at the liquid junction is called as a liquid junction potential, which is being abbreviated as LJP and which is denoted as EJ. The EMF of such cell can be given as E cell is equal to E1 plus E2 plus EJ, where E1 and E2 are the single electrode potentials. That means we can consider that of a zinc electrode potential as well as a silver potential, and EJ is, of course, as I said, is the liquid junction potential. Now the salt bridge can be used for reducing the EJ value, because EJ is considered as an interference. Okay, so as less the value it is, it can be neglected, so that the E cell value we can just get it as E1 plus E2. Alright, so it can be, salt bridge can be used for reducing it, if not completely being eliminating it. Which one? The liquid junction potential. Alright, so this is, my dear friends, about chemical cell with transference and without transference. Now we go into the next category, my dear friends, and that is electrode concentration cell, which is reversible to cation. If you remember, we have two types of this: reversible to the cation and reversible to the anion. So we first begin with reversible to the cation. We have an electrode over here, and that is platinum as behaving as an inert electrode, but then we have the hydrogen gas having a different pressure. Okay, so let's consider the left hand side as P1 bar and the right hand side as a P2 bar, and we have an electrolyte, that is HCl, of course, which contains H plus ions. So we first of all, as usual, consider the left hand side reaction, then the right hand side reaction. Left hand side reaction, generally we consider it as anode, where there is oxidation taking place, loss of electrons, and the right hand side is going to be a reduction reaction where there is gain of electrons, and then the summation of these two will give you a net cell reaction, and then depending upon the net cell reaction we go for the Nernst equation. This is what the pattern that we are going to follow, my dear friends. So let's begin with the left hand side reaction. We go for half mole of the H2 gas will lose an electron and thereby result in the formation of a proton, and the same electron which is being lost at the left hand side electrode is being gained by the proton, and that gives you a half mole of H2. But my dear friends, please be very clear, the half mole of H2 which is losing electron has a pressure of P1 bar. All right, and the hydrogen half mole which is going to be formed as a result of the proton gaining an electron is going to be a P2 bar. Okay, so please keep this in mind. So both of them have got different pressure. So now we go for a net cell reaction, that is the summation, and we get over here on both sides we have got hydrogen, but please remember on the left hand side we have a P1 bar, the pressure of which of hydrogen is, and on the right hand side we have a P2 bar. So now we apply a Nernst equation. So we have E cell is equal to E naught cell minus of 2.303 RT upon NF into log of. Now as we say, it's basically product upon reactance. So we have P2 upon P1 and the coefficient of which goes to the power. So both of them have a coefficient as half. So P2 upon P1 raised to half. Now here we have E naught cell is equal to 0. Okay, because we consider the electrode, electrolyte are considered to be same. Okay, I mean the composition is going to be the same, so we consider E naught cell as 0. So applying that into that equation, now the Nernst equation gets reduced to another form, which is E cell is equal to minus of 2.303 RT upon NF log of P2 upon P1 raised to half. Now I don't want that negative sign. Okay, I want to convert into positive sign. So there is one rule of logarithm, and that is I can change the sign when what I do is I convert the denominator into numerator and vice versa. So accordingly now what I get is a positive 2.303 RT upon F. The n value, now I consider it over here as half. So that comes on the other side. So it becomes 2F and then log of P1 upon P2. Okay, that negative sign is removed. So we have now log of P1 upon P2 because the numerator becomes the denominator and vice versa. All right. So now if the reaction has to be spontaneous, the condition you know very well that E cell has to be positive, and the E cell is going to be positive only when the ratio P1 upon P2 is greater than 1. All right, because then I get log greater than 1, and if log is greater than 1 then I get positive, and the overall E cell is going to be positive. So for that purpose P1 should be greater than P2 because P1 is a numerator, P2 is the denominator. So for the cell reaction to be spontaneous we need to have P1 greater than P2. All right, so I hope you have understood this part. We move to the next part now, and that is electrode concentration cell. Now it is reversible to anion. Now my dear friends, we are only changing the cell, otherwise the pattern remains the same. We have a left hand side reaction, we have a right hand side reaction, we have a NCR, that is a net cell reaction. We apply to the Nernst equation. Okay, so that pattern remains the same. So this is the beauty of connectivity, my dear friends. If you understand one particular cell, the second cell becomes very easy. So here we go. The cell is platinum, which is in contact with the chlorine gas. Okay, on both the sides, but only difference is that previously we had hydrogen gas, this time we have a chlorine gas with different pressures, that is P1 bar and P2 bar, and here we have an electrolyte is NaCl. Now, the left hand side is the chloride ions from the NaCl is going to lose an electron, and that results in the formation of a half mole of chlorine gas. And that electron is going to be accepted by that chlorine gas to give a chloride ion. Only difference is, my dear friends, is the chlorine gas which accepts electron is having a P2 bar as the pressure, and the chlorine gas which is going to be formed in the first reaction due to oxidation reaction is having a pressure of P1 bar. So the net cell reaction, on addition of both the reactions, we have, of course, we have got half Cl2 and half Cl2 on both the sides, but on the left hand side we have the P2 bar, and on the right hand side we have a P1 bar. Now, as usual, Nernst equation, E cell is equal to E naught cell minus 2.303 RT upon NF log of, this time it's going to be P1 upon P2 raised to half. Previously we had P2 upon P1 raised to half, now we have P1 upon P2 raised to half. E naught cell is going to be 0 because the electrode and the electrolyte are going to be same. Only thing is there is a difference in the pressure, that's it. So the Nernst equation now reduces to E cell is equal to minus of 2.303 RT upon NF into log of P1 upon P2 raised to half. Okay, now here we consider n is equal to 1, so that is going to be ignored. And then as usual, as I said, I don't want the negative sign, so as a result of which what I do is numerator becomes a denominator and vice versa. So I get E cell is equal to 2.303 RT upon F log of P2 upon P1 raised to half. That half goes on the denominator side, so it becomes 2F. So E cell is equal to 2.303 RT upon 2F log of P2 upon P1. Now, the condition for spontaneity remains the same, and that is E cell has to be positive. And E cell will be positive only, my dear friends, when the P2 upon P1 ratio is greater than 1. And that's going to be possible only when P2 is greater than P1. Alright, so everything remains the same. Only difference is going to be, my dear friends, and that is in case of reversible to cation, we had the final condition, and that was P1 greater than P2, and here we have P2 greater than P1. Alright, so this is, my dear friends, about electrode concentration cell reversible to anion. Now we go into the next part, and that is we talk about the electrolyte concentration cell. In this cell, the same electrolyte with different concentration is in contact with each other. Okay, now resulting in a liquid junction, because if the concentration is different, the speed of mobility is going to be different. Okay, and as a result of which, because of that, a potential is going to be developed, and that potential is called as a liquid junction potential. Now let's understand the origin of this liquid junction potential. So let's consider an electrolyte, that is HCl, having different concentration. One is diluted and the other one is concentrated, which are separated by means of a porous separator. Now, since the concentration is different, there exists a difference in concentration, which we call it in technical terms as concentration gradient. The electrolyte HCl dissociates into H plus and Cl minus. Since HCl have a different concentration, the concentration gradient leads to the flow of ions from a region of higher concentration to a region of lower concentration. You know this, my dear friends, very well. This is the basics. Now, as a result of which, the H plus ions are going to be smaller and they are lighter than Cl minus, and the mobility of H plus is greater and it moves towards the dilute solution, giving a positive charge. The Cl minus ions remains in the concentrated solution, giving rise to a negative charge. So on one side there is a positive charge where there is going to be H plus. On the other side there is going to be a negative charge because of the Cl minus, and this results in an electrical double layer. One layer of positive charge and the other layer of negative charge, which is going to be at the junction between the two solutions, and which results in a potential. Therefore, the liquid junction potential is nothing but the potential developed at the different concentrations which are in contact with each other. In this case, the EMF of the cell can be now represented as E cell is equal to E1 plus E2 plus EJ. This is the simplest form of showing the electrical double layer. If you can see, on one side we have HCl diluted, on the other side we have HCl concentrated. On the HCl diluted, you can see the positive ions and positive charge, that is because of H plus ions, and on the HCl concentration side we have negative ions, and that's because of the excess of Cl minus. Now, as I said, it is very difficult to accurately determine EJ value. I don't say it is not possible, but then it's difficult. And if you don't have the EJ value, the final E cell value will be slightly difficult, because the formula of E cell is what? E1 plus E2 plus EJ. So in order to get an accurate value of E cell, our perspective, our objective is to minimize as much as possible the EJ value. If we cannot completely eliminate it, but if we can just minimize it to as low as possible such that it can be ignored, then I guess we get almost a correct value of E cell. So how to do that? So let's consider now elimination of liquid potential junction. The junction potential can be eliminated by making use of a salt bridge. Now, my dear friends, what is a salt bridge? Salt bridge is an inverted U-shaped glass tube which is being filled with a saturated solution either of KCl or KNO3 or ammonium nitrate. which is going to be suspended in an agar-agar gel. Now, because it is a gel, once it cools, it sets. And that's the reason we can make an inverted use of that U-shaped glass tube. The use of KCl or KNO3 or NH4NO3 is because the transport number, that is the mobility which we are talking about, of the cations and the anions are equal. Hence, the flow of charge will be equal in magnitude in both the directions. And hence, as a result of this, there is no separation of charges. Okay, and therefore the liquid junction potential is reduced to a considerable extent, if not completely eliminated. And that is what I said. Okay, our motive is to reduce it to such a considerable extent that it can be ignored. Now, what are the functions of the salt bridge? First, it reduces or eliminates the liquid junction potential. Next, it allows the indirect contact. It's not a direct contact, my dear friends. Okay, we consider the two cells separate. Okay, so it allows the indirect contact of the two electrolyte. It does not allow the direct transfer of the electrolyte between the two half cells. Okay, it takes place via the salt bridge. Okay, it also makes sure that the electrical neutrality is maintained. That is, whatever the number of positive part is going from one side to another, equal number of negative ions are also going in the opposite side, and as a result of it, the electrical neutrality is maintained. And as I said earlier also, there is no separation of charges. Separation of charges is called as polarization. So it's not, it basically ensures that there is no separation of charges, and that's why we say it prevents polarization. All right, my dear friends, so this is the first part of the title of the chapter, and that is Applied Electrochemistry, where we have discussed up to the electrode concentration cells. Okay, in the next part we will be discussing about electrolyte concentration cells and Teffel's theory, and what are the factors affecting Teffel's theory and all that. So I hope, okay, this particular video is very clear to you, and I'm very sure question based on this you are very confident and you can very well attempt it. So thank you very much, and at the same time, all the very best to you all.